All right, so we're going to play around with Simpsons Rule. So partway through section 6, in chapter 8, they have at the bottom of one of the pages, Simpsons Rule, which is approximating with parabolas. And interesting thing about a parabola is if you have 3 points that aren't collinear, you can find a parabola that passes through them. Okay, so they show an example of one there. Since I need 3 points to make a parabola, for my Riemann sum, that means I need to do 2 intervals at a time. So my n has to be an even number. I have to have an even number of intervals to have parabola after parabola after parabola. Okay, so that's a catch. Whereas with right-hand endpoints, left-hand endpoints, upper sums, lower sums, midpoint rule, trapezoidal rule, they all can have, n can be anything, odd or even. You can do 4 intervals or 5 intervals or 10 or 11. With Simpsons rule, it's got to be 2, 4, 6, 8, 10. It's got to be an even number of intervals for it to work out. And then I'm not gonna go over the details of Simpson's rule. If you want to look at the algebra of how the formula for Simpson rule comes up, they give a really nice explanation here of solving the system related to finding like A, B, and C coefficients of a quadratic. But it turns out all we really need to know is how the y values of our function affect that parabola. And it turns out you can use a little bit of algebra and totally get rid of the A, B, and C, and you can write what we need about the parabola in terms of the y values in question. Okay, so I'm going to state Simpson's rule in a couple of different ways. If you want the details of where it comes from, check out page 489. Otherwise, we're just going to apply it. Oops, it's not Simpson with a Y, it is Simpson with an I. So it is rather a clever trick how you can rewrite the parabola in terms of the y values of the function that you're interested in. And so one version of Simpson's rule, you end up with h over 3. Remember with trapezoidal rule, we had h over 2. Okay, and then you get, let's use y values instead of function values. It looks cleaner. You get y sub 0 plus 4 y sub 1 plus y sub 2. So for any interval, any pair of intervals, this is what Simpson's rule leads to for the 3 x values that you need that bound the interval, right? So remember, if we have x values, x0, x1, x2, each of those leads to a point on the curve. Those 3 points break this up into 2 intervals, right? And then our goal is to try and find a parabola that goes through those 3 points. And it turns out to make that happen, all you have to do is consider the first y value plus 4 times the second y value plus the third y value. And it just works out nice like that. So that's the first grouping. And then you just keep moving along, and then you grab the next group of y values. Well, the next group of y values has to start where the other one ended. So it's going to pick up with x2 and then an x3 and then an x4, which is going to lead to y2, y3, and y4. So the next grouping will be y2 plus 4, y3 plus y4. Notice every time that evenness that I was talking about, right? Because we got to grab 2 intervals. 0 is an even number, 2 is an even number, 2 is an even number, 4 is an even number. Always works that way as you move along. Okay. And so you just keep adding these up. In the end, the last one down the line, that's usually what we call B on the number line, which is the last x value, the nth interval, the end of all of your endpoints. So the last one is going to have a y sub n. What's right before y sub n? n minus 1, right? So there'll be a, before that, there'll be a 4 y sub n minus 1. And before n minus 1 would be n minus 2. So you'll have a y sub n minus 2 there. So this is one version of Simpson's rule. And again, n has to be even. So the first few homework problems, they said let n equal 4. Well, that means you just have this little group in the top to deal with. Okay. H, remember, is the total distance of the interval divided by how many pieces you have. So in general, H is always going to be b minus a over n. The width of the interval divided into n chunks, right? Because it's a Riemann sum. We've been doing that since the beginning of the quarter. Now notice there's some repetition here. The endpoint on the right in one of these groups is the beginning point on the left. And so those are always going to line up like that. So I'm going to have to double those guys. So you can clean this up algebraically. So another version of Simpson's rule looks like this. You still have your h over 3 out front. The first y value only gets used once. The second one gets used 4 times, essentially. Because of that repetition in endpoints, y2 is going to get used twice. And then, as we saw earlier, y3 got used 4 times. So I have a 4y3. But then, let's see where to go. This ending y4 is going to be the beginning of the next chunk. So it appears twice. So you get this alternating 2, 4, 2, 4, 2, 4 moving throughout Simpson's rule. So it's going to be a plus 2y4. And then this just keeps going all the way to the end. At the end, the last endpoint only gets used once. So at the end, we're going to have a y sub n. Right before that, according to Simpson's rule, we had 4 times that middle one, always 4 times the middle one. This way, so I'm going to have still that 4 times y sub n minus 1. And then if you think about it, just like the previous example, that got used twice. This guy here is going to get used twice because it's adjoining 2 different parabolas. And so you'll have a plus twice that y sub n minus 2. So the point here is there's a pattern. The first and last y values get used once each. In between, it always goes 4, 2, 4, 2, ending with a 4. Always looks that way, right? So for example, if someone says, hey, n equals, I can only do 4 subintervals, that's all I have time for, then it would be whatever h is over 3, and then you would have y0 plus 4 y1 plus 2 y2 plus 4 y3, and then n is 4, right? So then I'm done. Why? The last one only gets used once. If somebody says, well, I have time to do 6 of them, then it would be y0 plus 4 y1 plus 2 y2 plus 4 y3 plus 2 y4 plus 4 y5, and then I'm just about out of stuff, right? Because I only have 6 things to work with, 6 intervals. And so there's my single y sub 6 at the end. So all we need to do is calculate the y values and then just add them in this weighted manner. And that's all Simpson rule breaks down to. So the parabolas sound kind of frightening at first, but it turns out it really works out to just some simple arithmetic. Okay. Okay, so that gets a little bit trickier. So I'm not going to prove how I come up with it, but I'm going to write down the formula for Riemann sum because you know, if somebody said I need 100, I don't really want to write out 100 y values like that. Okay, I could program a spreadsheet to do it. I could write a little program to do it otherwise, but since most computer systems have some kind of sum sequence option, a Riemann sum would be nice. So the Riemann sum version, new page. Consider that n is even, right? And if you look at the groups of stuff, you get your y0 plus 4, y1 plus y2, and then you have your y2 plus 4, y3 plus y4, and then you have your, what would be next, y5. So I'm just going to write it in a slightly different order to kind of see the pattern. Plus 4, y, let's see, did I do that right? 0, 1, 2, 2, 3, 4. Oop, that should be a 4. Because each one has to pick up where the previous one left off. That would be a 5, and this would be a 6. And right, we could just keep going depending on how many we had there. So for my Riemann sum, I need to add up 3 function values. Okay, so that's going to be important. So when I build my Riemann sum, I'm going to have that h over 3 hanging out front, and then I'm going to have, I'm going to write it in terms of, yeah, I guess I can use the y's. So there'll be a y value here, plus 4 times some y value there, plus a y value here. And I got to figure out, what do I call each of those y values there? Okay. So if n is even, that means n has to equal 2 times some other whole number. Let's call that k for a minute. N here is going up to 6. So note 6 is really 2 times 3, right? And over here, that's 4. 4 is really 2 times 2. And then 2, I consider 2 times 1. So these numbers right here are my k's. If 6 comes from 2 times 3, how could I write 5? It would just be 2 times 3 minus 1, wouldn't it? So 5 can be considered to be 2. Oops, that's not a pen. 2 times 3 minus 1. So for the k's, so an even number is always 2 times something. An odd number is always 2 times something plus or minus 1. That came up in the beginning of the quarter. We were playing around with Riemann sums. So what I'm going to do is, instead of having this sum be based on m, and I'm going to have it based on k. I think is that what I decided to do. Let me double check my other notes. I had 2 different ways to write it down. I was trying to decide which is the best one. And I typed it up last night. Ooh, that's awfully tiny. Simpsons Rule. Oops, that might work. All right, I called it J here. I'm gonna use K. So here, I'm gonna have the interval as K goes from 1 up to 3. And the key there is, since n is even, K is always n over 2, right? If you solve that for K. So I need to go up to whatever n over 2 is. The last number is always just 2 times whatever k is. Isn't the middle subscript always 1 less than that? Yeah, so that's got to be 2k minus 1. And this one is always 2 less than whatever's on that side. So that's got to be 2k minus 2. So that would be the Riemann sum version of Simpson's rule. It's a little bit trickier because you got to work with odd and even numbers. So you have to have a slightly different counter to make that happen. So for small numbers like n equals 4, n equals 6, n equals 8, it's not too bad writing out stuff like that. But if someone says to go past like n equals 10, I think I'm probably going to choose that method right there. And I just have to really carefully type that stuff into whatever system you're using. But you can do it. Another note on parabolas, in terms of using a parabola to approximate something, suppose I have the function 1 over x, whose antiderivative is the natural log, which is rather a weird function. 1 over x has the point 1, 1, right? And the point 2, 1/2, and the point 3, 1/3, about there. So it swoops down through those points like that. If I wanted to find a parabola going through those 3 points, it's really not that bad. I would just say, well, y equals ax squared plus bx plus c. And I just need to identify what a, b, and c are. To do that, I know I have the points 1, 1, 2, 1/2, and 3, 1/3. So this is kind of an outline of how they come up with Simpson's method. I'm only going to go partway through it. So if I plug in x equals 1 up here, then I get 1 squared. That leads to just an a, plus b times 1 is b, plus c has to equal the y value 1. So I end up with a system of equations to mess around with. And if you look on that page in the book, you'll see them set up a general system like this. But they use, x0, y0, x1, y1, x2, y2, and so on. Here, if I square 2, I'm going to get 4 a's plus 2 b's plus c has to be 1/2. And then if you plug in 3, you'll get 9 a's plus 3 b's plus c has to be 1/3. And if you solve that system, I played around with it this morning, I came up with a has to be 1/6, b has to be -1, and c has to be 11/6. So you could either use whatever method, substitution elimination, or just plug it into one of those matrix solvers we used for the partial fractions, and you get those coefficients. And so I plugged those into GeoGebra just a few minutes ago when I was testing it to see what it looked like. And if you zoom in here, you'll notice the red thing is the parabola, the green thing is the natural log, and notice it fits pretty tight in there. And again, let's see, make you go away. I'm looking in between x equals 1, x equals 2, and x equals 3. That's where I'm focusing there. And see how it fits pretty tight. Here, my parabola is an overestimate. Here, it's an underestimate. Okay, so there is some error involved in the approximation, but parabolas are super easy to work with compared to crazy things like 1 over x. Okay, and when we tried to find a Riemann sum for 1 over x, we were unable to take its limit. We didn't know what to do with it. Okay, so we had to rely on other tricks like fundamental theorem of calculus. But does the fundamental theorem of calculus always provide us with an antiderivative? The answer is it does not. Right? And so that's why we need these approximation rules like Simpsons rule and others, because, for example, you guys know the sign of pi over 2, right? What is it? It's 1. And the sign of pi over 4? Square root of 2 over 2. You can prove those with a little bit of geometry, but how do we figure out what's the sign of 1? How does somebody calculate that? Well, I got a button on my calculator. Okay, well, how does the calculator button do that? Somebody had to program it to calculate those numbers. How the heck did they do that? Well, they did it with numerical tricks like this. Okay, so somebody had to write these programs that figure out what is the sign of 1, what is the sign of 1/2, what is the sign of 3 pi plus 17. and those algorithms people developed have evolved over time. So Simpsons rule, although it is a pretty good approximator for definite integrals that we don't have antiderivatives for, there are better methods. They're just way more complicated and harder to describe, but they work faster and better. Okay. And there's courses like later, if you ever got really into math or programming, where you just study these numerical algorithms and how to make a better one, right? So there's always that balance with complexity and speed that people are working with when they're trying to solve these kinds of problems. But somebody had to write the program so that when you push that button, you get numbers that make sense, right, and work out. And so Simpsons rule is one way that happens. All right, so let's apply it to one of the homework problems. So I did a few of the homework problems here for you. So example 1 is like problem 1 on your homework. Example 2 is like problem 2. Example 3 is like problem 3. Example 4 is like problem 4. And apparently I didn't finish that one. So let's do that one. All right, what's that? Yeah, so it turns out with a line, so notice with Simpson's rule here, we have an overestimate there and an underestimate here. With a line, they perfectly cancel out. So I know with a line, like, why would we use Simpson's rule on a line, right? It's just a simple geometric area. I don't even need calculus for that. But so it turns out with Simpson's rule, with a line, with a parabola, with a cubic, there's zero error, which is kind of cool. Things just work out really nice. Yeah. So we'll do, so again, in resources is a link to this page here if you want to take a look at it later. I didn't finish typing up example 4, so let's do that one together right now. This is like problem 4 in the book. So I've got the integral from 3 to 9 of 4 over s squared with 4 subintervals. So let's build Simpson's rule. All right, so we want to calculate integral from 3 to 9 of, I forgot, was it 4 over s squared? Yes, 4 over s squared with 4 subintervals. So 4 over s squared with respect to s, n is equal to 4. So the first steps in this are like the way we did Riemann sums. We should do a little sketch of this, and we should also calculate our h. H is always the width of the interval, so 9 minus 3, divided by how many subintervals you want. So that's 4. So 9 minus 3 is 6. 6 fourths reduces down to what, 3 halves, or 1.5 if you like decimals. So that's what our h is here. Quick sketch of this is going to be helpful. So this is, let's see, 1 over s squared is a lot like 1 over s, but it's steeper toward the axis and steeper toward the y-axis and shallower toward the x-axis. So I'm going to say it looks something like that right there. And it's asymptotic over here to y equals 0. And let's suppose this is where 3 is, and if that's 3, 6, 9 is probably somewhere over here. So I'm zoomed in on this. If we plug in 3, for example, we get what, 4/27ths? And if we, we get 4/9ths, sorry. And if we plug in 9, that would be what, 4 over 81. So my scale isn't very good. I'm just going to go with it. And we are breaking this into 4 subintervals. And so sometimes I draw those right in here, cut it in half again, so I can see where they are. So we're going to end up with how many parabolas here when we do this? 2 parabolas, right? Because and remember, n's got to be an even number to use Simpson's rule. So we're going to have some parabola through here and another parabola through there. Okay, we don't actually have to calculate those parabolas because Simpson's rule simplifies that process for us. So all we need to know are what are the y values. Okay, so Simpson's rule says that the area here, actually I should list those x values. The x values that we're interested in are in the set starting with 3 and then jumping by 3 halves, which is 1.5. So the next one will be 4.5. Add 1.5 to that gives me 6. Add 1.5 to that gives me 7.5. Adding 1.5 again gives me what, 9? Yep, that works out. So that's my set of x values that I'm plugging in. So Simpson's rule says the area is approximately h over 3. So 1/3 of h, which is 3 halves. That'll simplify a little bit. Times your first y value. Well, to find a y value here, I have to plug in my x value. So my first y value is 4 over 3 squared. Simpson's rule says take 4 times the next y value. Next y value is going to be 4 over 4.5 squared. And then the collapsed version of Simpson's rule says take 2 times the next value because it appears twice. So then I'll have 2 times 4 over, next one is 6. And then it says go back to the 4 times 4 over 7.5 squared. And then the last one only gets used once. So that's just a 4 over 9 squared. So that's Simpson's rule there. And remember, it always has this alternating. First one gets used once, then it goes 4, 2, 4, and then it's got to always go 4, then 1, because of the way the parabolas line up. And then it's a matter of just plugging this into a calculator. So let's whip it into a calculator, see what happens. So Google, please, calculator. So let's see, 1/3 of 3/2 is 1/2, and I had started typing that, but I didn't finish, times, let's see, what's next? It was 4 over 3 squared plus 4 times 4 over 4.5 squared plus 2 times 4 over 6 squared, 4 times, oops, that's not times, 4 over 7.5 squared. Hopefully I type all this right. And then plus 4 over 9 squared. And Google's telling me it is 8.89 something. I typed it right, 0.895. You got that too? Okay, so hopefully we both typed it right. Can't remember how many decimal places it asks for. This is what, number 4. Number 4 said round to 4 decimal places. So the computer would want 0.8953. Oops. To 3 decimal places. Now, there's also an approximation of the error that you can get here, which is a wee bit complicated, but we're going to take a look at it. Okay, so here's the part about the error. So Simpson's rule, so again, here, H again. Simpson's rule says that the error, so S is for Simpson, you'll see an E sub T, which is error for the trapezoidal rule. There's a formula for that in the book also. Says to find some number M, multiply it by the width of the interval to the 5th power, divide it by 180 times N squared, where N is how many subintervals we have. How do you find M? To find M, you got to get the 4th derivative of your function and find an upper bound for that. Like what's the biggest the 4th derivative gets in your interval? Okay. Now, if you think about a linear function, the first derivative of a linear function is just a constant, and the derivative of a constant is 0, right? So our bound on the error for a linear function is 0, okay? So we have to find the 4th derivative of our function and go from there. So let's do that next, check our error here. M is the biggest the 4th derivative can get. And I stated that wrong. It's not equal to, it's less than or equal to. I better fix my notes. I knew that didn't look right. All right, so let's see if we can find our 4th derivative. So f of x is equal to 4 over s squared, which I think I'd prefer to write as 4 times s to the negative 4. So the first derivative, what's that? Negative 2, oops, yep. So negative 2. So the first derivative is going to be 4 times negative 2, so negative 8 times s to the negative 3, because we dropped that power by 1. f double prime. Negative times a negative is a positive, so 24s to the negative 4. Third derivative, 4 times 24 is what? 80, 96, negative 96, s to the negative 5th. And the fourth derivative, and usually once you start using like little dashes, either people use Roman numerals or they put a number in parentheses. So you could call the fourth derivative that right there. The book is writing it as parentheses, fourth power. And it's not the fourth power, that's why it's in parentheses, it's the fourth derivative. So we got to be careful there. Negative times a negative is a positive, 9d6 times 5 is 480 maybe, okay? And negative times negative is a positive, I already said that. So 480 s to the negative 6th. This is a decreasing function, right? Like 1 over s is, 1 over s squared is, they're decreasing. So we should be able to check the left-hand endpoint to find m. So here, the max, which is what m stands for, I believe is going to be equal to 480 times 3 to the negative 6th power, whatever that turns out to be. So altogether, if we take a look at the error function said find that max, okay, and just, I better double check that I'm right there. So if I graph GeoGebra, let's get a new screen. Yeah, you want the highest value of the fourth derivative in the interval is what you need to find. And sometimes that's easy to do, sometimes it's not easy to do. So what do we have? 480 times x raised to the negative 6th power. Looks like that. Yeah, so it's definitely a decreasing function. So fourth derivative value of it at 3 is bigger than at 9 over here. So back here. And so then, so as far as my error goes for Simpson's rule, it's going to be that number right there. It's going to be less than or equal to 480 times 3 to the negative 6 times the width of the interval to the 5th power. So my interval was what, 6 wide from 9 to 3. So times 6 to the 5th power over 180 times n, I forgot which power n was 2. N is to the 2nd power. And n for us was 4, is that what we did? 4 subintervals? So times 4 to the 2nd power. So we got to calculate that number right there to get our bound on the error. Because each time you do these, the computer will say, okay, use the trapezoidal rule, what's the error? Use Simpson's rule, what's the error? Or what's the bound on the error? So whip out your calculator. So in this case, let's see if I can remember this, 480 times 3 raised to the power negative 6. And then I have a times 6 raised to the power 5 divided by 180 divided by 4 raised to the 2nd, 1.777. Anyone else getting that? Which comes out to 16/9. Sure. So that's the bound on our error. That's a pretty big number compared to our, let's see, what did we calculate for our, oh, wow. The error is bigger than our actual number. Huh. Let's see, did we do that right? Oh, n should be to the 4th. I was looking at the wrong place. I knew that 2 didn't look right. All right, so it should be 4 to the 4th power. All right, back to Google. So 4 to the 4th It's better. Okay, yeah. It should be smaller than the number we came up with, but not always. Sometimes stuff like that happens. The number you're finding is so small, the error can get away from us, but usually it's going to be smaller. So we get an error of about 0.1111. How many decimals did they want? They said state the error to 4 decimal places also. So our answer is within that, right? So it could be that much lower, or the answer could be that much higher. Yeah, no, it was 0.89, 0.8953, I think it was. So let's see. Oops, I want you back. Yeah, 0.8953. So what we can say based on this error analysis, let me just write this in there. So that is approximately to 4 decimal places, 0.1111. So what we believe now is we think the answer is about 0.8953, but we could be under by 0.11111. So it could be if we add that on, let's see, what are we going to get when we do that? We'll get a 4, we'll get a 6, that 9 bumps up, 0, 0, 1. So it could be the area could be as high as 1.0064, or it could be as low as, take that away. So if I subtract the 0.111, it could be what, 2, 4, 8, 7. It could be as low as 0.7842. So the actual area should be somewhere in here. Now, a couple of other notes about this error approximation. We found that the actual error is 0.1111 about. Often what's more important than the actual amount you were off is what percent off is that. So we usually calculate percent error too. So to get percent error, you just take the amount of error and divide by what you think the answer is, 0.8953. What do we get when we do that? What is it? Sorry, about 12%? Okay. Give it to me too. Let's see, how many did they ask for percent error here? They did ask for percent error to 4 decimal places. So what are the 4 decimals? So 0.12, what? 1241. So about 12.41%. And in the homework, do they want it as a percentage? It's not quite clear how they want that in there. Let's. Round to 4 decimal places. Yeah, it's not clear from the printout I made whether they want that or as a decimal, 1241. So we're about 12% off. So it could be lower, it could be higher. Yeah, so the procedure for Simpson rule, anytime you do one of these, whether it's a Riemann sum with right-hand endpoints or the trapezoidal rule or Simpson's rule, you definitely want to make a sketch to see where you're at and break up your interval and identify the x values that you need. If it's right-hand endpoints, there's no weighting of the terms in between. With Simpson's rule, you alternate with a 4, 2, 4, 1 on each side. With trapezoidal rule, it's 1, 2, 2, 2, 2, 2, 1. Okay, so trapezoidal rule is kind of similar to Simpson's. You get a different multiple out front. With Simpson's rule, it's h over 2. Simpson's rule is h over 3. Trapezoidal rule is h over 2. Do multiple Riemann sums? Yeah. Oh, do a Riemann, so maybe, are you thinking do a Riemann sum for each of these guys here? Like the columns? Yeah, you could totally do that. Yeah. Yeah, and for bigger n, we would want to use this version of it, which is just a little trickier to deal with because you have these crazy x values that you're going to have to plug in. Okay, so that gets a little harder. But the homework doesn't have you do any big ones, so you're not going to need that formula. You going to try it? Yeah, it's interesting. You just got to be super careful when you're typing stuff in because you get some pretty complicated expressions with each of these. All right. So I'm going to stop there. We'll do some more with Simpsons Rule on Monday. And this homework assignment is relatively short. It's only 8 questions, but each question has like 6 parts. So, yeah, so.